So there's a bell for them to leave. There's a bell for normal people to be in class. And then there's a bell that says all of the MCA people should now be in class. But it's not a bell. It's Mr. Nash's voice going, everyone should now be in class.
Is there a bell that says listen to
really
Mr. Bergkamp?
It kind of scares me sometimes. Ferguson will be like talking.
Okay.
Yeah.
Okay. So here's the plan for the day. Yes, the Queen Mom has passed away. In case you haven't heard. It's all the rage. It's funny, I'm like 56 and she was Queen like before I was even born. So it's kind of a weird thought if you think about it. Kind of job security though. I mean, you know, what do you do? I'm the Queen. Oh, really? Good for you. Okay. She like that now. Okay. All right. So we're going to go over that assignment, make sure everybody's cool with that, because vectors are such an important part of this class. And then it turns into a good news, bad news day.
Oh.
So we're going to talk about forces, I'm going to do some demos, things like that, but you're not going to have any homework tonight.
Yes.
Okay, we'll start with, we'll actually do a lab starting tomorrow, which will take a couple of days. So that's kind of going to be the sequence. All right. So with these vectors, and we're going to use vectors so much with momentum, with forces, with electric fields, with magnetic fields, with optics, okay? So you have to get really solid on this concept because we will use this so often. So let's say look at like number 13 and 14, okay? So I just want to make sure everybody's kind of cool with this process. And like I said, you look at my answer keys, here's the charts, okay? It isn't like, hey, I'm going to make you guys draw the charts and I don't, right? Look at my answer keys. Here's all the charts. And the reason that I do those charts is because of the fact that it's going to alleviate mistakes and it's going to force you to keep everything organized. Now, this will actually start talking about free body diagrams tomorrow when we talk about that lab. So when you draw all the forces acting from the center, this is what's called a free body diagram. So one of the things that we talk about, like for example, we're going to say, okay, here's Keaton sitting in his chair. And it's like, okay, well, let's talk about the forces that are acting on Keaton. Okay, well, he's got gravity pulling down, and we'll talk more about this tomorrow. This is just kind of an introduction. And then we have F sub n, and that stands for a normal force. Okay? So normal force is basically what's provided by a surface acting up to balance out the force of gravity. So if I were to draw all of those forces acting on Keaton from like the center of his mass, okay, I've got gravity pulling down, I've got the chair providing an upward force balancing that out. That would be an example of a free body diagram. But if I take this glass and I push it like this, okay? Push it like this. Now that's much more dynamic because then I've got the force that I'm applying to make it move. I have friction going in the opposite direction. I've got gravity pulling it down. I've got the normal force acting on it, okay? So, but when I ask you to draw free body diagrams, I'm going to ask you to draw a lot of them, okay? Just keep in mind, you're going to draw all the forces acting from a common center. But what that's going to do is that it's going to give you an idea of what the net effect of this is going to be. So if you look at on number 13, so on number 13, you got one angle that's at 60 degrees, and the other one that's at 80 degrees, okay? So here's what's happening. We got Lily kicking the ball here at 60 degrees. We got Vitor kicking the ball at 80 degrees simultaneously. Where's the ball going to go? Somewhere between 80 and 60. Somewhere between 80 and 60 degrees. Closer to 80, closer to 60.
Closer to 80.
Closer to 80. Why?
Because it has more force.
That has more force. So that's the advantage of this. Oh, I know that my angle has to be somewhere between 60 and 80, and probably closer to 80 because 80 is the bigger force. Okay? So that's the advantage of drawing that free body diagram. So you're going to go through and notice on all of these, I've given you 3 significant digits on every measurement that you have. So all of these sub-calculations of your x and y components should have a minimum of 3 digits, okay? Some of you are like rounding this like to 0.5 or something like that. I went through great pain and suffering, not pain and suffering, but through great effort, how about that, to give you 3 digits in all of these measurements, okay? So when you're doing these sub-calculations of x and y components, make sure that you are having those 3 digits at least in those as well. So because both of these are, so there's your 5 Newton, there's your 10 Newton, and there's your sum. So because both of these are in that first quadrant, you know the x and the y of everything is going to be positive values because both forces are in that first quadrant. So you don't have to guess anything, boom, do the angles, there you go. So what you should see on number 13, that angle should be in the mid-70s, okay? Which kind of hopefully makes sense. Oh, okay, yeah, right. We said it would be closer to 80 than 60, it is. And that magnitude on number 13 should be around 15, and that's an ish, okay? But it should be something around 15. Now, 14 is a little bit more complicated, okay? Mainly because of the fact that you have vectors that aren't in the first quadrant. So, but again, you can overlay that same thought process. You go, okay, hey, I got a 5 newtons at 100 degrees. I got 10 newtons at 200, okay? So Keaton is kicking the ball this way at 100. Aspen is kicking it that way at 200. But it's the same thought process. What do you know about that angle? What does it have to be between? Somewhere between 100 and 200, okay? Because that ball is going to go somewhere in here, right? So right away, just by making that sketch of that free body diagram, you have an idea of what that angle should be, okay? It has to be somewhere between the two of them. And again, because of the fact that this 10 Newton force is bigger, that angle is probably going to be closer to 200 than it is to 100. So just by that, doing that sketch, you will at least have an idea, is your answer right? So this is where this gets a little sketchy, literally. So on this one, you got a 5 Newton force, you got a 10 Newton force, and then you have the sum. What is it, Lily?
Dude, I've gotten at least 20, 30 spam calls today. It's terrible.
But you do not disturb on.
Yeah, just turn your ringer off, bro.
Turn my phone off. So,
Or just start blocking them.
Oh, I can't block all of them.
No, but that's what I found though. As soon as I would block them, I mean, my number of spam calls dropped dramatically.
Oh, yeah.
So, because it tends to be like the same number.
Yeah.
So, just a thought. Okay. So, here's the deal. Now, just look at the signs. So, this first vector is in this second quadrant. So, what do you know about the sign of the x component? That's going to be a negative value. Your y component is going to be a positive. Now, again, you can do this one of 2 ways. When you look at that 5 Newton force at 100 degrees, you can roll it straight into using 100 degrees, sine and cosine. Okay, you can do that. If you're old school and you want to work off that 80-degree angle and then find the x and y components off that 80-degree angle, it's the exact same answer. It's just a personal preference in terms of how you want to do the problem. The advantage of the 100 degrees is that your calculator should automatically make that a positive and negative value. Okay? The disadvantage is the conceptual side of going, oh, if I choose 100 degrees, it's tough to see that, oh, this is the side opposite of 100 degrees. Okay? That's conceptually the difficult part. The mathematical part is easy. You slam numbers into the calculator. But if conceptually, it's easier to see if you use that 80 degree. Oh, I'm finding the side opposite of 80 degrees. Oh, I'm finding the side adjacent to 80 degrees. Okay? You pick whichever one works best for you. Okay? I don't care. Just go with that. Now, on that other one, because it's in the third quadrant, what do you know about those x and y components? They're both going to be negative. So right away, I know that my x component is going to end up being a negative value. Okay? I don't know about my y component because it depends on which one is bigger. Okay? So what you should see, if you do this right, you should get a negative x around 10, and you should get a y value around 2. Okay? So on number 14, that should be the sum of your x component, something around negative 10, and your y component is around 2. Okay, that's an ish. Now, here's the most important thing you have to do. I beg of you to do this next step. Come out here and make a sketch. And go, okay, here's my negative 10 newtons. Here's my positive 2 newtons. Boom. There's my result. Okay? Make that sketch. Okay? So that way you know which quadrant this thing is in. Now, this is where your calculator lies to you. You're going, oh, Mr. Again. It will completely roll you under the bus. Because somebody take the inverse tangent of 2 over negative 10. Let me know what you get. Let me know what your best friend tells you.
Like negative 10 degrees.
Your calculator says the angle is negative 10 degrees. Now, if you put that as your angle,
Because I know it is.
what am I going to do? Okay? I don't know. I don't know what negative 10 means. I don't know if that's below zero, like negative 10 here. Is that negative 10 here? Is it relative to my x-axis? Is it relative to my y-axis? I have no idea what negative 10 means. Doesn't make any sense at all. However, this is what I would do. I wouldn't even worry about that negative sign. I just find this angle. I just take the inverse tangent of 2 over 10. Your calculator says, hey, that's 10 degrees. Okay? Now I know that's 10 degrees, or whatever that is. Right? But if this is 10 degrees, how am I going to define that angle then?
It's 1/7.
Yeah, because my angle has to be defined from this positive x-axis. So if I can find this angle here, if it's in that second quadrant, if I can find this angle, I'm going to subtract it from 180. If my angle is here, I'm going to add that to 180. Okay? So that's the advantage of making that sketch. Okay. Are we good on that? Going once, going twice? So staple the diagrams to the back, put that all together, and get that handed in.
What did you get?
10.38.
What?
171.
On the money.
Actually,
10.38.
171.53.
Okay.
I didn't show any work for my
You'd be using that off-brand.
I don't know.
Using that off-brand Chromebook calculator.
These are just lecture notes, don't put them out.
Right, Camp, you gonna pop out tonight? The game?
No, actually, I've got a line judge in volleyball match.
Oh, volleyball.
Who's playing?
Us, Newton, and one of the Andover schools.
Who's better, Major myself?
Thank you.
Are you a biased line judge?
You're biased.
Not at all. Not even if they brought you peanut M&Ms?
No.
Oh, I would be.
I used to lie judge all the time. And then I haven't line judged in probably 10 years. And then they came in and said, hey, we're really desperate. Can you come out of retirement? It's like, all right, fine.
Do players get mad?
Huh?
They yell at you what? No.
I just turn around and scowl. So,
You calculate the velocity of the ball.
Like, do you really want to argue physics with me? Do you really want to? Come on. Especially because I'm going to be dressed like this. It's like, do I look like I'm incompetent?
That's what you wear while you're blind judging?
Yeah.
Really? No way. Like sitting
You
up
don't have
there?
like a jersey?
Huh?
You don't have like a jersey, like a striped one?
You sit
I might take the top. I might loosen up the top.
and you sit up there in like the little booth thing?
No, this is line judge. Like, you got to be down there on the court.
But he's just crouched down.
Yeah, it's
like
like
full three-piece
Focus.
suit.
Focus.
That's cool.
I would not
Okay.
argue with you.
He's a
I enjoy it, but if I hadn't done it in a long
If
time.
you're a soccer ref, I would never argue.
Huh?
I'd never argue with you.
Soccer
If you're a
ref in a suit.
Red card.
Yeah.
Okay.
All right, see you. Okay. All right, so let's chit-chat about forces. So, the cool thing about forces is that everybody kind of knows what a force is. But if I said, okay, what's a definition of a force? What would you say?
A force.
What'd you say?
Like you're pushing on something?
Like I'm pushing on something. Like, I push the apple. Okay? So that leads to the next question. Does every force require physical contact?
No.
No.
No. What's an example of a force that doesn't require?
Magnetic field.
Gravity.
Well, gravity.
Yeah.
Okay. Electromagnetic. Okay, like a magnet. Okay. All right. So not all forces require contact. Most of them do. So if you look at the forces that you experience in your life, holding a pencil, writing with it, okay, typing on a keypad, turning a steering wheel, your car tires being in contact with the road, okay? But everything that you experience in terms of forces does require contact, okay? The only time that you have a situation where there really isn't contact is like you said, like with gravity. Oh, okay, I throw something up in the air. Oh, it comes back down. Now, for a while, they thought gravity was magic. No, and I'll tell you why. It's like, what do you mean magic? Okay, so let me give you an example. Let's say I take that apple and I put my hand above it, and all of a sudden the apple began to levitate upwards towards my hand. Okay? You all would go, he's a wizard. Okay? A Jedi. Something, right? Or at least you would say it's magic. So why would you say, if I put my hand here and that apple began to levitate up towards my hand, why would you say that's magic?
Because you're not touching it.
I'm not touching it. It's moving and it's not touching it, right? No physical contact. Oh, it's magic. But if I hold this apple up and I drop it, oh, that's gravity. So if you apply that matrix that says it's magic because I didn't touch the apple but it moved, if it goes up, you're going to burn me at the stick because I'm a witch. Okay? If I drop it and it falls, oh, that's just gravity. Okay? So that's why you have to be careful about how you define what's magic and, oh, what's just a law of physics. So one of the things we'll talk about, this is all these lecture notes that I gave you, is there's 4 fundamental forces of that we call basically they sorted through all of the forces and they said, okay, look, let's classify them into 4 general classifications. 2 of them are the ones that basically dominate your life. So the first one I want to talk about is gravity. So, and we'll go through this calc. Do not write this down right now. Okay, I'm just showing you this equation. So to calculate the gravitational force between 2 objects, it's F is going to equal big G M1 M2 divided by distance squared. So we're going to spend days talking about this equation. Okay, this is just the opening solvo. So this big G is what we call the universal gravitational constant. It's a number. We'll talk about it later. Okay? It's a really, really small number. 6.67 times 10 to the negative 11. These are just the two masses, and this is how far apart they are. So this is what's known as an inverse square law. We're going to study a whole bunch of different laws that what we call an inverse square law. So what that means is because the distance is squared, if I double the distance, what's going to happen to the amount of force?
Quadruple.
Not quadruple.
1/4.
It'll become 1/4 as much. Okay? Because then, so that becomes 2d squared, so that becomes 4d squared. So instead of dividing by d squared, I'm dividing by, so what this means is that as objects get further and further away, gravitational force between them becomes weaker. So gravity has been called like the great sculptor of the universe. Because if you didn't have gravity, we wouldn't be here having this discussion, okay? Because if you look at the sequence of events that happened after the Big Bang, then you had pure energy. That energy had to cool down. As that energy cooled, you began to form matter out of that energy, okay? And the first thing that you began to form was hydrogen, okay? That was the first element. Basically, you had a proton and an electron. So out of that, because it had mass, you had a non-homogeneous distribution of mass after the Big Bang. And thank God it wasn't completely, if it was completely homogeneous, we would never be here having this discussion. So there were some wrinkles, and some of that hydrogen became more concentrated. And as that hydrogen became, that gas became more concentrated, it started creating like this cycle. Oh, as that clumped together, that created more mass. As that created more mass, that created a stronger gravitational field. That drew in even more hydrogen. That, oh, big party over there with that star. Oh, let's go hang out over there. So then it began to draw more and more hydrogen into it. As it drew more and more hydrogen into it, the mass got bigger and bigger and bigger. So it just became like this downward spiral. Oh, more mass, stronger gravitational field. It pulls in more matter. More matter, more stronger gravitational field. Oh, that pulls in even more matter. So eventually what happens is that you start a diffusion process, okay? Hydrogen fuses together, it takes tremendous high temperatures, tremendously high pressure. The short version is, we'll give this whole lecture on in the spring. Basically, 4 hydrogen atoms combine to produce helium. That's the first generations of stars. So if the universe never had gravity, we would never be here having this discussion, okay? The only thing that would exist in the universe is hydrogen gas, protons and electrons. That's it, okay? Now, conveniently, the universe did form protons and electrons, because if you think about it, if the universe had just formed protons, we wouldn't be here having this discussion, because you could never form complex molecules, okay? Everything would just be repelled by each other. If you just formed neutrons, okay, that's kind of cool. Neutrons are pretty neutral. Okay, hence the term, right? We wouldn't be here. If you just formed electrons, we wouldn't be here. So conveniently, our universe, for whatever reason, made 3 particles: protons, electrons, and neutrons. It actually made a whole lot more. Okay, there was like 40 some odd. Okay, it's called the standard model of particle physics. We actually have like 40 different particles. That's the short version. Those are the big 3 that you're used to talking about: protons, electrons, and neutrons. You get into muons and all this weird up quarks and down quarks, and it gets really weird really, really fast. But, so when you look at gravity, star-to-star formation, basically the stars blew up, they went nuclear, okay, they exploded. That then created like the next generation of atoms. That's when you began to get lithium. That's when you begin to get carbon, nitrogen, oxygen. So all of the atoms that make you up, anything beyond hydrogen, all formed in the deaths of previous generations of stars. So it's this old cliche, and it's kind of cosmic, it's kind of hippie-ish. But it's the absolute truth, is that we are all made of stardust. So all of the iron in the hemoglobin in your blood, all of the nitrogen, carbon, oxygen that makes up your DNA, okay? All of those atoms at some point were formed in the collapse and deaths of previous generations of stars. Those stars went supernova, they exploded, all of that material got kicked out. And then it got reformed, and here we are in G20 at 10 till 2 in the afternoon, talking about star formation and the fact that we're here. So it's kind of this is pretty philosophical if you think about it. We are a collection of atoms that knows that we're a collection of atoms, okay? If you think about it, that's pretty profound. Because everything else, oh, here's an apple, that's a collection of atoms, doesn't know that, okay? We have to be a collection of atoms that knows that we're a collection of atoms. Okay, I know what you're all going like, what happened to physics? Oh, it got real philosophical real fast. I don't know what's going on, but I'm an atom and I know I'm an atom. Okay, so I don't want you to think about it too much, okay? And that is the old joke. Once you really delve into what happens on an atomic level, like with protons, neutrons, and electrons, it gets so weird so fast. And if you think about it too much, I jokingly say you'll just end up doing drugs. Because or at least you're going to be in the corner sucking on your thumb going, I have no idea what's going on. Because atoms are extremely weird, okay? They're actually like 99.9% empty space. And you sit there and go, wow, that's not empty space. Sure it is. On an atomic level, that's empty space. If you took an atom and compared it to the size of like the Kansas City Chiefs football stadium, if that was the size of the atom, that's empty space, except for a softball in the middle of the 50-yard line, and that's where all the mass is located. Okay? Everything else is literally empty space created by electrons moving around. And you're going, no, it's not. Yeah, it is. Okay? For mostly empty space. And here's the other weird things that you do this, and you say, what happens? Your hand touched. No, you've never touched anything in your entire life. Okay? You have never touched anything. Because the electrons that make up this hand don't like the electrons that make up this hand. And they actually, you think you're touching? No, not. The electrons don't even like electrons in the same hand. Because if they liked each other, I would do this, and then part of the skin might stay on the palm, and I lift this up, and it's like, oh, that's awkward. Okay, I've lost my fingerprints. Where are your fingerprints? They're on the palm of my hand. Weird, okay? So, that's why I said, atoms do weird things. So, one thing I want you to get out of gravity. Number one, it's always attractive. You don't have to like get your phone out in the morning and check your gravity app and go, oh man, gravity's repulsive today. Oh, that's going to change how I do everything, okay? Gravity is only attractive. We don't have to worry about getting out of bed and gravity pushing you towards the ceiling, okay? Which would be weird. It's like I dropped this and all of a sudden the apple starts to go. It's like, okay, that wasn't planned. So, the other thing is that the only thing that has to happen is that you have to have mass, okay? That's all. You have to have two objects that have mass and a distance between them. So what that means is that you can never be in a state of zero gravity. The only way you can be in zero gravity, and this is the ultimate freshman mentality, the only way you can be in zero gravity if you literally, you are the only thing that exists in the universe. Like there is nothing else, okay? If there is mass anywhere else in the universe, you will be gravitationally attracted to them. So this is kind of like a cosmic connection. So you're obviously attracted to this big rock that we're on, okay? You're also gravitationally attracted to the moon, to Saturn, to the sun, to the most distant galaxy. Massive black hole in the middle of the Milky Way galaxy. You are gravitationally attracted to that, okay? You're gravitationally attracted to the fire extinguisher on the wall. Now, that's not a strong force. I don't have to worry about all of a sudden I'm in the middle of lecture and I see Carolina starting to float over and be attracted to the fire extinguisher, okay? If that happened, there'd be a whole bunch of other issues that are taking place. But she is gravitationally attracted to that fire extinguisher. You all are, okay? It's kind of this cosmic thing. Now, everybody thinks, oh, gravity is a really strong force. In reality, gravity is actually the weakest of all the forces. And that's a good thing. Because if gravity had been much stronger, you could have been theorized that you would have had like the Big Bang, but if gravity was stronger, you would have turned around and then you would have had like the big crunch. Because the universe would have went whoop, whoop, okay, back in on itself and we wouldn't be here having this discussion. So gravity is like in this Goldilocks zone. Gravity was weak enough to allow for the expansion of the universe. but it was strong enough to start hydrogen and start star formation. So if gravity was too weak, we wouldn't be here having this discussion either, because you would have never started the fusion process in stars. So gravity is in this Goldilocks zone for us to be here having this discussion. So here's all the thing I want you to remember. If you have objects that have more mass, they have a stronger gravitational field. The closer they are, the stronger the gravitational field. The farther apart they are, the weaker the gravitational field. That's all I'm going to expect you to know for that. Now, the second one is what's called the electromagnetic force. Sometimes you'll see it called the electrostatic force. Okay? Now, to calculate this, and we will spend a lot of time using this equation as well. So to calculate the gravitational force between two, listen to me, charged particles. This is just a constant. Okay, don't worry about it. It's just a number. And then you have Q1, Q2 over d squared. These are charges. Okay? Now, you have protons, electrons, neutrons. Neutrons are never put into this calculation because neutrons don't have any charge. So, the cool thing about this, and I'll show you this in just a second, is that that force could be attractive or it could be repulsive, depending upon the situation. And these are just the values of the charges. And again, do not write this down. In the spring, we'll spend a huge amount of time talking about this equation. But these two charges are measured in coulombs. Okay? It's called a coulombic force. But again, here's the cool thing about this equation, is that if you look at this equation relative to the gravitational force equation, they share a lot of similarities. They both have some constant, okay? The gravitational constant is 10 to the negative 11. This constant is 10 to the negative 9. They're both small. You have mass, which is a fundamental property of the universe. Both things have mass. This is charge, fundamental property of electrons and protons, right? They're both inversely proportional to d squared. So mathematically, these two equations look very similar. So this was the idea of what's known as the grand unification theory. And Einstein was big into this. And so the idea being is that could we not take all of these different equations and unify them into one? And the idea being is that it was called like the T-shirt equation test. It's like, could we explain the existence of the universe with one equation that we could print on the back of a T-shirt? Okay, that was kind of the test. Like, we're here because of, and then there was an arrow that would point to the back of the shirt and says, oh, this is why we have water, this is why we have penguins, this is why we have squirrels, okay? Because of this equation right there, and everything is explained, okay? But the problem is that when you get into an atomic level, gravity and the electromagnetic force are incompatible with each other, okay? They don't like each other, they don't play nicely. So this is why we haven't been able to reconcile these into one big, grand, unified idea. So give that camera a little bit of a spin. So what I have here is your basic balloon hanging from the ceiling. Now, if I put my hand there, okay?
One like these.
Yeah.
But he just wanted to flash his
Okay. I thought you were going back there.
No. We will go back there. Okay. I'm kind of working my way around. So now, if I put my hand here, my hand has a certain amount of mass. The balloon has a certain amount of mass. Okay. So there is a certain amount of a gravitational attraction that exists between me and the balloon because everything has mass, right? Not a lot. Okay. There's a little bit. But if I take that balloon and I rub that with hold on. I can put my balloon back in.
Hold up. Ooh. Wait a minute. You should rub it like that. Okay.
Well, it's done.
Yeah.
Oh, God. It's sticky. I used to have clips up here, but they got taken out. Hold on.
We believe in you.
Cut the cameras. Cut the cameras. Cut the cameras.
You're just like,
Okay.
sure. Vitor just filmed me without consent.
Vitor's vlogging.
What?
Vitor's just vlogging over here.
Sideways. Mad crooked camera.
This thing's like broke.
I wonder who worked the camera last, Vitor.
Not me.
Don't fall.
Matt's already attracted to your shirt.
Oh. Okay.
It's magic.
Well,
Burn him.
this works better if the air is warm and dry. She'll get the idea.
Whoa.
Okay? Now, so clearly, something different is happening, right?
Yeah.
So, does anybody here ever had like a Chihuahua as a pet? Or know of someone that did?
My neighbor.
Okay. How would you describe Chihuahuas? Annoying,
Terrible.
right? Okay, they're tiny, they're yip, 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 okay? And then they go running away, hopefully. So, electrons are like the Chihuahuas of the atomic world, okay? There's a lot of them, they're tiny, and they run around in little herds, but we don't like them. So, but then you have also St. Bernards and like German Shepherds. They like chill out. They're these big, massive ones, but they're pretty chilled out. So basically, here's the short version again. We'll spend days talking about this. When I did that, when I wrote that balloon on the blanket, the little Chihuahuas jumped from the balloon to the blanket. So now what's happened is that the balloon has excess Chihuahuas. Okay? This is important. The balloon has excess Chihuahuas. Now, my hand is neutral. All of us are neutral. It isn't like we're charged particles, because that would be really awkward if we were. It's like, oh, everyone's negatively charged. Well, that just means we're going to repel each other. So overall, we're neutral, but we're made up of charged particles. So basically what happens is this. Why this is happening is because the Chihuahuas that make up my hand don't like the Chihuahuas on that balloon. Okay? So when I bring them close, the Chihuahuas that make up my hand, they migrate away because they're little and they can run away. Now, the nucleus is made up of these big, massive St. Bernards and German Shepherds. They're like, you know, we're just chilling out. Okay? We're not going anywhere. We're big, we're massive, we're not going anywhere. And the Chihuahuas go, yip, 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 and they go running away. Now, the St. Bernards have this big positive charge, right? So when I put my hand here, the Chihuahuas go, oh, we're out, yip, 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 gone. The positively charged particles that still remain in my hand are going, we kind of like the Chihuahuas. They're kind of cool, okay? And this is a mutual attraction. So when I do this, the Chihuahuas that make up my hand go running away. But it's left with a net positive charge. That net positive charge is attracted to the negatively charged particles that are on the balloon. And it doesn't matter, it isn't just my hand, right? Okay? I can do this with anything of me that has made up of atoms. And it's always going to happen. So I do this, okay? It's like, ooh, it's magic. Now, if I take another balloon and do that, okay, then you get a little bit of attraction. But if I rub this balloon, now they're both overloaded with Chihuahuas, and the Chihuahuas are going yip, 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 yip on both sides, right? And they don't like each other. So now, charge this back up. So if I really overload them, they certainly don't like each other because of the fact that they're both overloaded with Chihuahuas. So this is an example of this equation, okay? So I have nothing happen when it was neutral, okay? There was no electrostatic force. But this is also a great way to show the influence of distance. So, give that a little bit. So, when I'm here, and the closer that I bring my hand, the stronger that force becomes, because I'm dividing by a smaller distance, okay? So over here, there's a little bit of a force, right? Not much, but as I bring my hand closer and I shrink that distance, that electrostatic force becomes greater. And the same thing is true of the repulsive side. So the closer that I bring this balloon to this one, the stronger that repulsive force becomes. So the only thing on either one of these that we can change is the value of the distance. So when you look at the force that defines your life, obviously there's gravity. But the electrostatic force is actually the one that really dominates your life. Because without that, we wouldn't have a toaster. We wouldn't be able to make electricity. Okay? We wouldn't have light. We wouldn't, and if you think about it, let's say, for example, you look at the simple act of taking a pencil and writing on a piece of paper. Okay, so one of the greatest things we've done as a species is to be able to control the electrostatic force. Because if you think about it, okay, you have a pencil. Cool. So the particles that make up that pencil are bound together. That's what makes it a solid, right? Makes them a solid. You can sharpen it, right? Not a big deal. Basically, it's carbon atoms. Then you go, oh, hey, I need to write the word force on my piece of paper. Okay. So then you take that pencil that's made up of those carbon atoms that are bound together, and then you begin to write on your paper. Fundamentally, what's happening is that on an atomic level, you are tearing those carbon atoms away from each other. And they're sticking to the paper. So that bond is strong enough to hold those carbon atoms together to make your pencil. But then when you write on it, then that bond with that paper is stronger than the bond to its other carbon atoms, and then it sticks to the paper. And you don't have to worry about, oh, I just wrote on my paper, and I do this, and then all of a sudden all the pencil lead comes falling off. It's like, oh man, you picked up my paper, I just lost all of my work, okay? Now, let's say hypothetically you make a mistake. What do? You take an eraser. How does that work?
Friction.
But what does it do? On an atomic level, what are you doing? Yeah, you're breaking the bonds that hold the carbon to the paper, okay? Because if you can't do that, it's like if I take an eraser and try and erase this ink that's right on here, guess what? Not going to happen, because that bond is stronger with the paper than it is to the eraser. But with the pencil, oh, cool. You go to wash your clothes. What's the function of the detergent in the dishwasher?
To make them smell good.
No. That's an added bonus.
Clean them.
What does it mean to clean them?
To get out stains and dirt.
Rip away the,
So what do you have to do?
rip away the stains or the sweat.
But on an atomic level,
Have a
what are you
greater
doing?
attraction.
You're breaking the bonds that hold the stain to the clothes. But you don't want such a strong compound that it breaks the bonds that hold the clothes themselves together. It's like, ah, man, that soap didn't work. You look inside the dishwasher, and it's like, where's your clothes? Oh, there's
Dishwasher.
Why are they in the dishwasher?
Yeah. It dissolved. I don't know what happened there. I thought it was okay.
Why are you using a dishwasher to clean clothes?
Huh? Or the
Said
washing
dishwasher.
machine. You know what I mean. Dishwasher. You can get a pinch, it could work, you know.
Yeah, it's just
Yeah.
top rack,
You
bottom
could,
rack.
I've taken the baseball cap and put it in a dishwasher.
I've never heard of that before.
Oh, yeah.
What? Could it shrink it?
No, but no, you can actually buy it's like a metallic, like a metal clamp that you put in your hat, you can put it in the dishwasher. Little known historical fact.
Where do you
Okay.
Very little, maybe.
So, when you look at, somebody said friction, right? You rub your hands together, okay? Generates heat. Heat is a form of electromagnetic radiation. We can't see it. We actually see a very, very narrow band of the entire electromagnetic spectrum. That's cool, okay? You've all, I'm guessing, hopefully at some point, done the Roy G. Biv thing, okay?
What's it?
Right? Red, orange, yellow, green, blue, indigo, violet, okay? Colors of the spectrum. Out of the entire electromagnetic spectrum, all the way from really, really long radio waves to very, very short gamma rays, okay? We experience and actually can see a very, very, very narrow band of that. And that's okay, okay? Because if we could see the entire spectrum, we would be like on sensory overload. Instead of like hearing a radio station, we would see a radio station, okay? It's like, it's kind of weird. What are you looking at? Country music? Okay? So, but radio waves, they all work on photons, okay? Photons are little bundles of energy, which we'll talk more about later. So, what we can do is, even if you look at light, we're going to spend a lot of time talking about optics. And light does some weird things. So, if you look at, let's say, for example, Louis has a white shirt on, okay? The reason that that appears as a white shirt is because it is reflecting all the colors in the spectrum, okay? It appears as a white shirt. Now, Pop has pretty much a black shirt on. That appears black because of the fact that it's absorbing most of the light, okay? Now, if you look, Keaton says a montage, my God, that's so many things going on. So if you look at like the reddish hues on his shirt, those appear that way because it's absorbing every color but that red. The yellow is absorbing every color but the yellow. So what you're seeing is actually the absence of that color. So when you look and see like my yellowish tie is absorbing all the colors, but it's reflecting those that you see. So this is why when it's hot outside and the sun is shining, if you wear a dark colored shirt, you get hot because of the fact that that is absorbing all of those photons. A white shirt is going to reflect those photons, and that's why that's cooler. So black absorbs it, white reflects it. So even if you look at something as simple as seeing, it's actually very, very complex as you have these little bundles of energy called photons. And so the electromagnetic force is the most diverse. It allows us to have electricity. It allows us to have light. It allows us to see things. It allows us to have friction. It allows us to exist. Because if we didn't have the electrostatic force that holds together and allowed atoms to bond together to make molecules, like for example, if oxygen didn't bond with hydrogen, we wouldn't have water. If we didn't have water, we wouldn't be here having this discussion, okay? So the electrostatic force is the most diverse of all the gravity. It's a one-trick pony. It's a good trick, don't get me wrong, okay? But gravity is kind of a one-trick pony. So we're going to go to the back. We're going to look at some different manifestations of the electromagnetic force. So stop that, unplug that, and okay, so what this is called a Van der Graaf generator. And basically it's like rubbing the balloon but on steroids, okay? So we'll take little bits of paper, put that at the top, turn that on. Whoa. Okay? So why does the paper fly off? Explain in terms of chihuahuas.
The ball has too many chihuahuas.
They both have way too many chihuahuas. So
There's way too many chihuahuas involved.
Yeah.
And guess what? They don't like each other.
They don't like
So
each
if you look at... No, I've done this God knows how many times in my entire life, and you know you're going to get shocked, but it's just like, oh, okay.
How bad of a shock is it?
Huh?
Like,
Well, it's a decent shock.
it's like whenever you touch a light switch that's not a cover on.
Oh, it's worse than that.
Worse than that?
Yeah.
Oh.
Okay, so what's happening is that you're building up a tremendous excess number of chihuahuas, okay? And so what's happening is that the paper then is taking this path of least resistance. So the chihuahuas are building up on the paper, and they're trying to get as far away from each other as they possibly can. So what happens is that that paper gets so overloaded with chihuahuas that it says, I'm out of here. And it's actually stronger than the gravitational force is trying to hold it down. Okay? Now, the other thing you can do is kind of demonstrate this. And this works better if the air is drier, but you'll get the idea. So we'll give this on. Okay? So now I can kind of do this Jedi mind thing.
Whoa.
Okay?
He's a witch.
I'm a witch. You turn me into a newt. I got that. Huh? So as this is going around, so why are these floating out?
Because they
have a lot of chihuahuas.
They have too many chihuahuas. So what's happening is that you're generating chihuahuas. Okay? And the chihuahuas want to be as far away from each other as they possibly can. So that path is going to take them towards the end. So when I bring my hand here, okay, you get a little bit of a distortion. So this is a situation where there's forces involved, but we're not touching anything. Now, if I do this, I'm going to take one for the team. Okay, roll this up. Got excess chihuahuas, a lot of them, right? Now, as soon as I touch it,
And nothing happened.
then the chihuahuas take the path of least resistance. The path of least resistance is through my hand and over the surface of my body. Now, because the chihuahuas aren't going to go through my body, it isn't like, what happened? Burkamp? Heart attack? Really, what happened? Chihuahuas.
Yeah.
Okay? Chihuahuas got it. Okay? I don't have to worry about that because I know that those chihuahuas are going to flow over the side of me. Now, chihuahuas also can generate other chihuahuas, or excite them, and make them make electricity. So if I take this, okay, and put my butt up. God, I wish the air was drier.
Maybe if Connor touches it.
Come on. Ah, there we go. A little bit. Okay, you see that flash of light?
No.
Right through here. Watch that.
It might be on your side.
Oh yeah, I saw it.
Okay?
Hey, get that zoom.
So what's happening
I see it.
is that the chihuahuas are
I can feel that. Can you feel that?
No.
building up.
You can feel it.
Okay?
Yeah.
And so as those chihuahuas build up, the chihuahuas flow through the bowl. They encounter the particles that make this up. They excite those chihuahuas. Chihuahuas, I'm guessing everybody had Chem 1?
Yeah.
Yeah.
Okay? So what happens to an atom to make it produce light? There's two things that have to happen.
The electron gets excited.
Moves out of
It's all
They
the ground state into,
excited state.
doesn't like it there, it
Jumps
jumps
back
back
down.
down. In the process, it gives off
Photons.
photons. Okay? So that's basically what's happening here. So the chihuahuas have a tremendous amount of energy. They flow into here, they encounter other chihuahuas, they give those the energy. Those chihuahuas go, woo, right? They jump out of their ground state into a higher energy state, they return back, they got to get off of photon, they got to get rid of that energy. That's what allows you to see that as light. Okay. Now, let's say that you need to pick up some little bits of paper. So, take this one.
Whoa.
Okay?
Magic.
Magic. Or chihuahuas, whatever the case may be.
Be a YouTuber.
Magic chihuahuas, okay?
I'm too
So,
cool to vlog.
why did this work? If I put my hand over it,
That's the first.
nothing.
Nope.
I put the balloon over it, magic. What's the difference?
chihuahuas.
Whoa,
Chihuahua.
whoa, whoa, whoa.
Big
Everything's made of
dogs.
Chihuahuas, St. Bernards, German Shepherds.
The amount.
Balloon has a lot of chihuahuas.
This has a lot of Chihuahuas. So what happens is that when I bring this, what happens, if you notice this, let me charge this again. If you look really close, okay, what you'll see is like that Chihuahua is like pointing downward. So the paper is made up of Chihuahuas, St. Bernards, everything is, right? So what happens is that you have a negatively charged part of the paper. That paper has excess chihuahuas. The other end of the paper has a deficiency of chihuahuas. So that end that has the deficiency of the chihuahuas is attracted to the balloon. So that's a small scale version of what happened when I put my hand in. Now the other thing that you can do, and this one I make no guarantees because the air might not be dry enough. So we'll take this can, put that there. And
ooh, roll.
magic. So, how can I make the can roll
Because
without touching it?
balloon has too
Chihuahuas.
many
Chihuahuas. What's the default answer? Chihuahuas. So, how do you have electricity? Chihuahuas. Why don't we have light? No chihuahuas. There you go. Now, let's go a little bit beyond chihuahuas.
Chihuahuas ran away.
What do you say?
I'm sorry. Chihuahuas ran away.
From what? From where?
Oh, they ran away from the can
to the
so
balloon.
That's right. So what's happening? Because if I just put this over the top, it isn't like the can's going to go whoop, okay? Which would be cool. Don't get me wrong.
Zooming in on it.
But if I do this, so it's like Louis said, what's happening is that, imagine you have all this excess chihuahuas here. The aluminum is metal, it's a conductor, which means that the chihuahuas move very easily through it, okay? So when I do this, the chihuahuas in this certain region of the can go running away. St. Bernards are left behind. St. Bernards going, so you, chihuahuas, we're tight, okay? They don't mind each other, they like hanging out. Because the chihuahuas are going, oh, cool, right? So when I do this, let me recharge this, because I lost two chihuahuas. So now when I try this, to make that, oh, come on, to make that roll, what's happening is that you're creating, we'll talk more about this later, something called torque. Torque is what you need to make things spin about an axis. And so by doing this, basically what I'm doing is that I'm creating as that rolls, then I'm shifting the location of the chihuahuas. So when I do that, that region that's attracted to the balloon here is continuously changing. And that's what's allowing that thing to roll, because that's always moving that dynamic where the chihuahuas are and where the St. Bernards are. Okay, got it? Good? Rand?
Yeah. Got it.
Back we go.
Can we touch it?
Yeah, they can stop it now.
Yeah.
Turn it off.
No, we still got more to do.
I'll bet. Fit check. Look at this. The polo, the white cat. Oh my god.
No. Bro, what are you talking
With
about?
socks, dude. You can't be barefoot.
No socks.
Nah,
They're
dude.
meant for no socks.
No, they're not.
Did you stop the recording?
No?
Whoever watches these recordings is probably pretty entertained.
Vitor's the
I
next
should be-
Logan Paul.
I should be a YouTuber.
Honestly.
It's about to start
Okay.
boxing, everybody.
Paul's out KSI.
So about what?
Nothing.
Some stupid thing. Guy goes from making YouTube videos to boxing everybody.
No problem.
It's a bit of an odd arc, but you know.
Don't listen to Louis.
It's just how things work
Alright.
nowadays.
Life.
So now we need to look at a bit of the history of science. Okay, so now we need to look at where we're at. So if you were to, and this is what we talked about yesterday. So here's a physics book from 1902. If you look in the index, there's no mention of protons, electrons, neutrons, chihuahuas, nothing, okay? At the time, the world was the scientific community was settled on the idea of an atom. So if you look at the Greek word atom, that comes from the Greek word meaning indivisible. Not invisible, okay, but indivisible. So if you go back and look at this, how this debate played out in ancient Greece, there's Plato, Aristotle, Socrates. Okay? So Aristotle was the most dominant of those. So basically, you had a group of philosophers that said the universe is made up of 4 elements. Anybody know what those 4 elements might be?
Air, water,
wind,
Earth.
earth. Okay? And that makes sense.
Avatar.
Let's say that you want to make a clay pot. What are you going to do?
Earthbend.
Huh? Where are you going to go to get the clay?
From the
From
ground.
the earth. Okay. I'm going to take some of the earth. I want to make a clay pot. You want to boil water. What are you going to do? You're going to burn wood, right? Okay. Where are you going to get the water from?
The river.
From the river. Where did the river get its water?
The ice.
Clouds.
From the clouds. Okay. From the air, right? Air gives water. Water goes into water or into the river. You take water from the river. You put it in the pot. You boil the water. Where does the water go?
The air.
Back in the air. Makes sense. Okay? You look at everything that you're wearing, all the tape, everything, right? At some version, this basically came from the earth. All we're doing is changing the manifestation of that location. Okay? That's it. Now, you had another group of philosophers that were oddly enough called the Atomists. Okay? Now, the Atomists, they had a different view of this. So, stay with me through this idea. So imagine this is a chunk of gold. Okay, so this I got the golden apple. Okay, so this is the golden apple. And I'm going to take this, and I have this infinitely sharp knife. I'm going to take this, and I'm going to cut this apple in half. Is it still gold?
Yes.
Yes. I take the other half, and I cut that. Still gold.
Yeah.
Right? And I keep cutting, and I keep cutting, and I keep cutting. At some point, I will not be able to cut that anymore and have it still be gold. So, in the atomist view, once you got to that finite particle that could no longer be divided and it still be gold, that's what they called an atom. Because there's an old cliche that the only thing that exists in the universe are matter and empty space. And there's some validity to that. Because if I were to cut through this, the knife would only cut in between the spaces in the atom. Just like if you're a football player and you're trying to run through the line, you're not going to try and run through where someone's standing. You're going to run through a gap. So when you cut that, that knife is going to go between the gaps. So if you keep cutting and you keep cutting and you keep cutting, at some point there's no gaps. It's just like this tiny, 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 tiny little Lego. Okay? And so, in their view, we exist as a collection of these little Lego blocks, okay? If we put the Lego blocks together in one set of instructions, we get squirrels. If we put them together in another set of instructions, we get Oreo cookies, okay? And the world is basically made up of these Lego blocks. So that's how they viewed it. So John Dalton, who was the first one to really come up with an atomic theory, and he came along and he says, look, the world is made up of atoms, and he went retro. He went back and he pulled that word from the ancient Greeks. Okay, so he was a student of history. He says, look, atoms are indivisible. They combine in whole number ratios, which is why the formula for water is H2O and not H3/4 O1/8. Okay, they only combine in whole number ratios. All atoms of the same element are identical. So like all nitrogen atoms are the same, all carbon atoms are the same, okay? And that was the basic idea. And that was done in the 1800s. And at that point, everybody was cool with that. And literally, throughout the entire kind of 1900s, and especially as you were getting towards the end of that, into the early, or late 1800s, early 1900s, the scientific community was actually kind of depressed. Because they thought they were kind of out of a job. They said, we had Newton's laws at that point, because Newton's laws were published in the 1600s, so you had Newton's laws. We understood gravity. We understood our solar system. We could predict when the moon was going to go into a solar eclipse and do a lunar eclipse. We could predict the path of the planets. The scientific community was literally depressed because they were like, we've worked ourselves out of a job. But there was nothing left to find out, okay? Because they thought they were done. So, a guy by the name of J.J. Thomson. Anybody know the subatomic particle discovered by J.J. Thomson?
Electron.
Electrons, okay? So J.J. Thomson discovered the electron. And he used a cathode ray tube, which we'll talk more about later. And so he discovered electrons. And so the important part is that the electrons have a negative charge. They're the chihuahuas, right? So then everybody got to think, it's like, oh, dude, if there's negatively charged particles, what else does there have to be? Positively charged particles. Because if the universe only was made of negatively charged particles, we wouldn't be here having this discussion. Because look what happened when I tried to bring two negatively charged balloons together. What happened? Oh, outie, right? We would never be here. You could not build a complex strand of DNA. You could not build a cell. You couldn't build a minnow, okay? You couldn't build an oxygen molecule because the two oxygen atoms would go flying apart. We wouldn't be here if the only thing that existed were negatively charged particles. They said, okay, well, there has to be positively charged particles, okay? So then they said, okay, well, what's the structure of an atom? Now, you have to remember, and this is important, so there's certain big players, so J.J. Thomson, Ernest Rutherford, Niels Bohr, Max Planck, Werner Heisenberg, okay? All of these people were physicists. They weren't chemists, okay? The chemists were over there trying to find a way to purify cocaine, all right? They had other fish to fry.
Meth.
No, that's a true story. At the time, in the early 1900s, you could legally buy cocaine, okay? You could. And so, but they figured out, well, this is highly addictive, we better regulate that. So the physicists of the world were going, all right, we'll take on the challenge. So the first model that they came up with, and you have to keep in mind that this was done in England, specifically University of Cambridge. So the first model that they had of the plum pudding, of the model, is what's called the plum pudding model, okay? So they basically viewed the atom as a Lego. And then they said, okay, we have some positive and negative charge that's evenly distributed within the Lego, okay? It's the plum pudding model, look at us. Or do that in honor of the Queen, God rest her soul. So they conceded that there were negative and positively charged particles, but they said there was an even distribution of them. Because no matter what the model was, you had to be able to explain the stability of atoms. So like, I've been teaching behind this desk since the fall of 1994, okay? Fall of 1994, I've been teaching behind this desk, okay? 28 years I've been teaching behind this desk. When I walk in this room every morning, there's a lot of things that I worry about. How are my kids going to do? Things like that. What I don't worry about is this thing turning into a squirrel, okay? I'm not going to walk in one morning and go, oh man, my table turned into a squirrel. Now what am I going to do? Okay? It's not a concern, okay? I worry about a lot. It turning into a squirrel, not on my list, okay? This thing has been a table, and it's been a table for longer than you all have been on this earth, okay? It's stable. It is, okay? Gold, okay? Gold is formed in the collision of neutron stars, okay? Massive black holes collide. That's how you make gold. And they're stable, right? If gold wasn't stable, we wouldn't use it in jewelry. So whatever the model is, has to be able to explain the stability of an atom. So the plum pudding model worked because they said, okay, they conceded that there were positively and negatively charged particles. This balanced it out. You had some repulsion, you had some attraction, you had some, give and take, yin and yang, however you want to put it, but it was stable, and that was cool. So then they gave this to the physics department, specifically by a guy by the name of Ernest Rutherford. Ernest Rutherford was actually from New Zealand, and he was this big guy, had a huge, big personality. Everything about Ernest was big, and he was a physicist. So if you remember what he did, so Ernest Rutherford did what was called the gold foil experiment. Anybody remember that from Chem 1? Okay. What he did is that he had a radioactive source, which we'll talk more about later. And out of this shot alpha particles. Alpha particles, they didn't even know what they were. Turns out they were a helium nucleus without the electrons. Okay? So it was called an alpha particle. They didn't know what they were. But here's the classic example of how physicists approach the problem. You give a Volkswagen Bug to a physicist, and you go, hey, what's the bug made of? I don't know. Let's run it into a wall. That would be cool. So you smash it into a wall at 10 miles an hour. Oh, look, there's a bumper. Okay, obviously there's a bumper. Well, if 10 miles an hour is good, 100 miles an hour has to be better. Okay, let's run it into 100 miles an hour. Oh, look, there's glass. Cool. Okay. Ooh, 100 is good, let's do 1,000. Oh, look, there was an engine inside of it. What's the engine made of? I don't know. Let's get the engine up to like 10,000 miles an hour. We'll smash the engine into the wall. Oh, there's pistons inside of the engine. What's the piston made of? I don't know. Let's get the pistons up to like the speed of light, and we'll smash the pistons together, and we'll see what the pistons are made of, and they'll go flying apart. And that's basically how physics works. Okay? On an atomic level, that's how physics works. You are smashing things together, and that's how particle accelerators work. Oh, what are protons made of? No, smash them together and see what comes flying off. So that's how Rutherford approached it. He says, let's smash things together and see what goes flying off. Okay, so we will take up Rutherford tomorrow. That's a good stopping this. So, you have the homework. So.